Welcome to video 6.2 in our first Principles of Astrophotography series. In this video we discuss image formation.
Image formation is crucial to astrophotography, but even the basics are poorly understood generally, and they're so interesting.
The video is based on section 6.2 of our first Principles of Astrophotography book, which is linked in the description below.
I'm Ren Edwards.
And I'm Boyd Edwards.
Let's talk sensor sensibility. Principle 95, image formation. Images are formed by creating a one-to-one correspondence between points in the field of view and points on the camera sensor.
So let's take an example of a blue star and a red star that are in different places in the sky. And we want to create an image of those two stars. If there were no lens, then all these light rays, I'm showing just 5 light rays, but they go out in all different directions from that blue star, and all those light rays would hit the sensor, and each pixel on the sensor would get light from that blue star. And so yes, you could tell it's blue because it's blue in color, but this sensor is going to give you no information whatsoever about where that star is.
And then you put a red star in there with, and then you just have a purple.
Yeah, then you just have a mush, all the pixels are purple, and you don't have an image.
Yeah.
So what a lens does is that it creates this one-to-one correspondence, or a mirror, or a combination of lenses and mirrors. That's what all telescopes do, and all cameras do. So now, with the lens in place, it takes all those 5 rays from the blue star, they pass through the lens, and then the lens's job in life is to take those 5 rays, or an infinite number of rays, and focus them down onto a single point on the image. That's what imaging is all about. Then the red star sends out all of its rays. All of those rays that pass through the lens come to, they converge at the same place on the image. So now, the pixel that's right here on your sensor, it says, hey, I'm getting red light. There must be a red object. Yeah, there might be a red star where in the corresponding spot in the field of view.
And in astrophotography, this is the lenses are so important because we have such dim, such far away, such point things. Stars are what we're looking at, and to perfectly replicate a point object on a sensor is difficult for lenses to do. But this is the whole idea of astrophotography, is to get that perfect correspondence of light to point on the sensor.
Exactly right. So now the light from the blue star comes through the lens, and all of that light that passes through the lens comes to a point on the sensor. And then this pixel on the sensor says, hey, I'm getting a lot of blue light. There must be a blue star in the field of view. Happy day.
Yes.
So in subsequent videos, we will point out that what we just described here is a lie. So sorry. Anytime you pass light through an aperture, it can never come down to a point. It comes to an airy pattern, and we'll talk about that with diffraction. The bigger the aperture, though, the closer this light comes to a point. And so what we're talking about here is called geometric optics in physics, and it's the first approximation, and a very, very good one. Because basically, most of that blue star light is going to end up at or very near a point. So
that's what we're looking for.
That's what we're looking for in order to make a nice sharp image. So if there's no lens, we talked about that case, all you're going to see on the sensor is gray mush. Same thing will happen with your eye. If you remove your cornea and your lens of your eye and just allow light to hit directly onto your retina, then you're just going to see gray mush. A mixture of all the colors in the field of view, but you won't have any definition whatsoever. Then the other question that we do when we teach this in physics is to ask the students what happens if you cover up half the lens. So suppose we put a piece of black paper in front of this half of the lens. That should mean that you won't be able to see the blue star, right? No, you'll still see both the blue and the red star, because you get this ray from the blue star, and all those that are next to it, it'll focus down on that point on the sensor.
They're still hitting that spot. Yeah.
They're still hitting that spot. The image won't be as bright because you're not receiving as much light from that blue. It'll be half as bright. The same thing with the red. The red light that is able to make it through the unobscured lens will still end up here, and you'll still get an image. So
this diagram is the reason that I understand why our Schmidt-Cassegrain doesn't have a hole in the center, because I couldn't understand. I couldn't get why if you put a hole in the middle of my eyeball,
yeah, it wouldn't make a hole in the image.
It wouldn't make a hole in the image, but this is why. This is why you don't get a hole.
So Ren's talking about our Celestron Edge HD 9.25, and it has, if you look through the front of the telescope, if this is the aperture opening like we talked about, there's a central obstruction here. So light can't pass through there. There's a mirror facing the opposite direction. But anyway, the only place you get light is through this, it's called an annulus, the region between two different circles. And Ren was asking, well, that should mean that the image would have a hole in it. Well, no, because if you cover up this part of this lens, so forget about that, and you're allowed to have light come through here and here, you'll still get an image formed on the sensor. It just won't be quite as bright.
Right.
Yeah, so now you know, and you can teach your grandkids how images are formed.
All right, principle 96, image plane. For distant objects, the image plane and the focal plane coincide.
Okay, so let's first talk about what we mean by the image plane and the focal plane. The image plane is where the image is formed. And if you're focused, that image plane will be at your sensor. If you're not focused, that image plane will be in front of your sensor or behind your sensor. That would be embarrassing.
Yeah.
Yeah. But that's where you want to form the image. The focal plane is at a distance of the focal length from the lens. So it's where that, we talked about this in the previous video, this is the focal point, and the plane is the plane that runs through that focal point. So obviously you can see in this diagram that the focal plane does not coincide with the image plane. The focal plane is in front of the image plane. But what we're going to do now is to show that for distant objects, those two planes coincide. And what you need for this, and there's more detail in our book, but is the thin lens equation. 1 over the focal length equals 1 over the image distance. That's this distance right here. And the image distance, di, is the image from the lens to the image plane. DO is the distance between the lens and the object you're looking at, these stars. So that's this distance.
Kind of big.
Kind of big. Like even for the nearest stars, that's 4.25 light years. So that's a very big distance. In fact, that is how we're going to use, that's how we prove this principle, principle 96, that these are two are going to coincide. If the object distance is large, basically it's going to infinity. It's humongous. I mean, between, like on the camera right there, the image distance is going to be between the lens and the camera sensor, which is a few centimeters. On our telescopes, they might be 1,000 millimeters or 100 millimeters. On the Sea Star, it's 250 millimeters, the focal length.
Yeah.
And but the bottom line is that the distance between the lens and the image, for almost all, well, for pretty much all astrophotography, that image distance is much, much smaller than the object distance DO. So if DO is going to be large, then from your basic math, if you take 1 over something that's huge, you get something that is
Small.
small. So if you take 1/2, that's not that small. If you take 1/100, that's pretty darn small. If you take 1 divided by 1,000,000, that's really small.
You're good. Yeah.
And so this guy becomes small compared to the other two terms in the equation. We're going to ignore that term, which leaves us with 1 over f equals 1 over d naught. And we can just cross multiply or invert and multiply, whatever your favorite way to do it is, to show that
I think that's this one now.
Oh yeah, that's right. So thank you. DO is large. This term gets ignored. Thank you for that. So we're left with this term. Thank you, Ren. 1 over di. And then cross multiply. You get 1 times f is f, and 1 times di is di. So this shows that the image plane and the focal plane coincide. So what does that mean? It means that as you take these stars way out farther and farther away, then this image plane will get closer and closer to the actual focal plane, and then the image will be formed at the actual focal plane. But there'll still be a point for blue, still a point for red. There's an orange star. You'll have a separate spot for it.
Yeah.
Thanks for that correction.
Nice. Yeah. Principle 97. Size on sensor. The linear size, d equals f theta, of the image of a celestial object on a sensor is the product of the telescope focal length f and the angular size theta of the object in the sky, with d and f in millimeters and theta in radians.
Okay. So this says that the size of this image is going to be equal to the focal length, f, that's this guy right here, times the angle of the object on the sky. And this one you can get it from simple trigonometry. There's a right triangle right here. So here's one corner, and one corner of this right triangle. And because the image plane coincides with the focal plane, then this distance here is going to be f. So you've got a triangle with an angle theta, and the image distance, which equals the focal length, right, because those two coincide, times the size of the image on the sensor. And you might say, this is still a little too much math for me, but this equation, we will refer to it over and over and over in the book and in our videos. It's so essential. It has to do with magnification of the image. It's just, there's just so much. The pixel scale equation, we'll use this to derive the pixel scale equation, P equals 206.3, capital P over F, etc., just so you want to know. But if you want to relate this angle to that side is opposite. And this side is the side that's adjacent to the angle. So we can use the tangent of the angle is the side opposite over the side adjacent. Some might write it as opposite over adjacent. That's what the tangent is defined as. And then if you multiply both sides by f, then you get f is I'm sorry, D equals F tangent of theta. And you say, well, hang on just a minute. That does not look the same as that. You should be very embarrassed,
Oh,
you say.
I'm embarrassed.
But I say, no, don't be embarrassed. Because the tangent of theta, for very small angles, tangent of theta is approximately equal to theta. And therefore D is F times theta. And you might say, well, those angles really aren't that small. And I say, yes, they are. The field of view through most telescopes is somewhere around a degree. I mean, for wide field telescopes, it might be 2 or 3 degrees. And for really high focal length telescopes, you're talking about half a degree or a third of a degree. Those are really small angles. And as we talked about in our video about angles, we talked about angular distances that, and we showed a picture of what a 1 degree angle looks like. And it's really, really small angle. And for very small angles, then the tangent of theta is approximately equal to theta, and D equals F theta is valid. Theta, however, must be measured in radians, and we talked about that in a previous video. It can be angles can be measured in degrees or radians, arc seconds, arc minutes, etc. But for this formula to be valid, theta has to be measured in radians. Thanks for watching.
And we'll see you next time.